Why is understanding life important? As human beings, we have a natural urge to understand other forms of life and a desire to know what an organism is experiencing. The earth is abundant in diverse life, and it is human desire and curiosity that draws us to discover and explore. For this particular story, we are drawn to the Namib Desert along the western coast of Namibia. The Namib, whose name means vast place, is said by some to be the oldest desert in the world. With sprawling dunes and an abundance of emptiness, it is easy to feel small and isolated. Traveling by four-wheel drive, our destination is the Gobabeb research station in the heart of the Namib. Students gather here from three very different parts of the world: Israel, Namibia, and the United States, to study life and landscape together. They come here from their universities: the State University of New York College of Environmental Science and Forestry, the Matrani Department of Desert Ecology of Ben Gurion University of the Negev, the Namibia University of Science and Technology, and the University of Northwest in South Africa. Students are given 10 days to explore, discover, and study the dynamic desert environment together. The experience begins with emergence into the landscape. Lessons are given on natural history and geography. Students learn that oxidized magnetite is what gives the Namib dunes their rusty orange color. They learn that the Namib is unusual in that it is a fog desert. Even though rain is very rare here, water streams into the desert as fog and humid air from the cold Benguela current that streams offshore. They learn the difference between fog and rain, and that fog will quench an animal's thirst, and that dew can give rise to new plant life. The influence of the fog extends nearly 100 kilometers inland from the coast. Students get to walk amongst Welwitschia, colossal plants common in the Namib whose lineage can be traced back to the origins of the flowering plants. Night walks with UV lights reveal the hidden world of dancing white lady spiders and scorpions. Their small bodies cling to trees and poke out of secret burrows. By the third day, students have formed into groups based on an organism and environment they wish to study. They set about to answer a specific question about how the organism adapts to the stark desert environment. 7 different groups were formed: Nara niche construction, white lady spiders and burrow environment, ant walking speed, lichens and moisture absorption and retention, Welwitschia niche construction, microclimates and crevices, and golden mole hummock interaction. The Nara plant is a member of the cucumber family, which makes it an unusual desert specimen. Their melons need a lot of water, but in the desert, where does the water come from? It's not just the Nara that depends upon this water. The plant's stems and fruit are food for animals such as the blister beetle and the Nara cricket. The Nara plant has evolved a taproot system that allows it to reach deep into the desert sand. The leaves have been reduced to thorns, reducing evaporation. This group's hypothesis was that Nara manipulates its environment by capturing energy and wind to build a hummock that can be several meters high. This creates a microenvironment more suitable for the Nara and the creatures that depend upon it. Students tested this idea by measuring the operative temperature, wind power, and capture of moisture in fog and dew, and compared the environment of the Nara hummock against the sandy plains nearby. Getting close to the ground, students measured the effects of temperature and solar radiation on walking speed of ants. Ants in the desert ecosystem are important animals because they disperse seeds and bury them in microenvironments where survival and germination are more likely. They also play an important role in soil aeration. The environment close to the ground is extremely hot. How did the ants that live there cope? The students' hypothesis was that the ants' walking speeds would be driven by sun. Shading walking ants should therefore cause an immediate response in walking speed due to the drop of solar radiation. The students manipulated the increments of radiation by using artificial shade, and compared walking speed in direct sun and shade. They also measured relative humidity and wind speed close to the ground where the ants live. Students determined that walking speed was affected by the extent of thermal radiation from the sun. As the sun rises and the desert sand begins to heat, ant walking speed increases. Eventually, the environment close to the ground gets too hot for the ants and their foraging activity ceases. This is important for understanding how this ecologically important species survives in the harsh desert environment.
We first started out looking at bats, but we changed the experiment quite considerably. We've seen bats flying in and out of these crevices here, so although they're quite difficult to reach. So we decided to measure the different microclimates in different crevices that they could potentially be roosting in. Firstly, we have made operative temperature models of bats, which I think you've already photographed, and we put them into the different crevices at different depths. We made little plaster models about the same size as our operative temperature models, and we soaked them in water. In the laboratory, we timed how fast it took for all the water to evaporate in very strong conditions, so wind, full sunlight. So we got to 9 hours. So then we deployed them in the different crevices and came back about 6 hours later, took them out and weighed them to see the difference of evaporation in these different microhabitats. Now we've just put thermocrons and hydrocrons up in some of the crevices, and we'll come back in 2 days' time and check the relative humidity and see how it fluctuates with the temperature over the different depths inside the crevice. We'll come back tomorrow with 2 hot wire anemometers, and we want to check the wind speeds outside the crevices and inside the crevices to see if any wind is eddying inside the crevices and if is any ventilation going on there.
Besides the implications for looking at bat roosts, it can also apply to other similar sized organisms to get a better understanding of the microclimate inside of the crevices and what type of environment animals who live there or choose to seek refuge there are living in.
This project is also going in concurrent with the tree bats, what we put the same sample what you have explained. It's also, we sample on the riverbeds that you can see.
In exfoliating
bats, yeah.
So the bats shove themselves up under the crevices?
They do, in the tree bark as well.
Yeah, the tree bark.
Well. Different species.
Okay.
So we're investigating all potential habitats. But then, like I said, we can then, it's also applicable to other organisms that would roost in crevices.
Lichens are unusual creatures. On the one hand, individuals, and on the other, an ecosystem. Namib lichens depend upon pulses of fog and dew for the water they need to live. Students looked at different lichen body forms to determine which species retained water for the longest period of time. Time-lapse imagery shows how lichens absorb and lose water. As the lichen absorbs water, it unfolds to expose the green photosynthetic microorganisms that live within. In other instances, the lichen greens and swells as it absorbs water. As the captured water evaporates, the lichen shrinks and blackens, waiting for the next pulse of fog. The lichens that absorb water the fastest are also first to lose water through evaporation. Lichens with a hard covering tend to absorb water more slowly. The third group, known as the spider group, investigated how the dancing white lady spider builds its burrow as a shelter against the desert conditions. Their burrow has a trapdoor. Does the trapdoor help the spider to regulate its burrow environment? The white lady spider lives underground during the day in a burrow constructed of sand and silk. They only emerge in the evening to hunt and search for mates, leaving behind a network of tracks scattered across the desert. The students hypothesized that the trapdoor is important for regulating burrow temperature, and also serves as a water source for the spider by retaining moisture from fog. Locating spider burrows was tricky as they are well camouflaged in the desert sand. Students located spider burrows by following their tracks. Once located, the burrows were marked with spoons. Using tiny data loggers placed inside spider burrows, students collected temperature data from burrows with doors and with the doors removed. Students determined the temperature in the burrow with an intact door remained constant through the day, whereas burrows with trapdoors removed showed greater daily fluctuation in temperature. Welwitschia is a unique desert plant, puzzling to scientists because of its huge leaves. Generally, desert plants have small leaves to keep temperatures low and to reduce evapotranspiration. Welwitschia's huge leaves seem to defy this rule. Why? Students set out to discover if Welwitschia uses its large leaves to create an environmental niche, its own cool and moist microhabitat that is different from the arid environment around it. Students use data loggers to collect temperature and humidity data from several different locations on and around the Welwitschia's immense leaves. Under the leaves, the environmental humidity is higher and temperatures are as much as 20 degrees cooler than the outside environment. The golden mole of the Namib lives by swimming through the sandy dunes. Very little is known of this intriguing species. Golden moles are small, blind creatures that are endemic to the Namib Desert. They rely on their sensitive hearing and touch to find food, mostly termites in the vast open areas of the desert. They do not inhabit permanent burrow systems, but instead they spend the daylight hours buried to depths of 5 to 35 centimeters in soft dune sand. Their tracks from the night before can be found in the early morning, writing a record in sand of their foraging behavior. When they dip their heads in the sand to listen for the vibration of the organisms they seek for food. When they encounter tufts of the dune grass Stipagrostis, where many tasty creatures live. How far they wander at night as they travel to find their food. The dune grass hummocks are also where golden moles spend the day. We measure soil temperatures within hummocks covered by plants and compare them to hummocks with no plants. And we measure relative humidity within the hummock and compare it to humidity in open area soils. Perhaps the hummocks provide moles a more humid microenvironment. The beauty of the desert is a universal language shared by students as they sit on top of the dunes in the evening to watch the setting sun turn the sand into a blaze of reds and pinks. There is a positive excitement to be here. An experience that leaves a lasting impression, shaping students into the people they will become. They are shaped not only as scientists and creative thinkers, but as people who can empathize and learn to see that the diversity of human experiences is the most important lesson to learn.